Okay, a very short video to send you into your weekend. We're going to talk today about this Bessel function of the first kind. That's a more general solution where v represents p, but v represents basically any value greater than or equal to 0. The general solution we talked about yesterday, that was the summation k equals 0 to infinity of -1 to the k, x to the 2k, plus v, and then the denominator contained 2 to the 2k plus v, k factorial, and then the gamma function of v plus k plus 1. Okay, well this guy has a number of differential properties where the function basically increases or decreases its value for the p function. So it's a way for you to basically take Bessel functions as if they were functions in and of themselves and look at relationships between them. So let's look at 4 of those differential relationships. Here's relationship number 1. Your book calls it A, but I'm just going to call it relationship 1. These aren't theorems and don't have specific titles. Okay, the first one is x to the v, j v of x. So that's the product of those two. And we're going to take the derivative of that, and that's equal to xv j of v minus 1 of x. So it's a way of basically transitioning the Bessel function in v to a full integer below it. Okay. 2 does a similar thing, just in the opposite direction. So it's x negative v jv of x, and it's the derivative of all that, and that's equal to negative x to the negative v j to the v plus 1 of x. So this will transition a Bessel function to the Bessel function immediately above it with a full integer value higher than v. And then these coefficients are just necessary. If you go ahead and do the derivations for these, you'll see that these coefficients basically come out as a result of the derivation. The index in the book, one of the indexes actually has these derivations. If you're interested in going through those, be my guest. Okay. And then the third one is a simple sum. This is the one that doesn't have a differential relationship, and it's basically kind of picking on these two over here. So jv minus 1 of x plus jv plus 1 of x, and that's equal to 2v over x times jv of x. So it's a way of indicating a non-differential relationship between jv and then jv plus 1 and minus 1. Okay, and then number 4 is the final differential relationship, and it also deals with both jv and jv plus 1. So it's jv minus 1 of x minus jv plus 1 of x, and then that's then equal to 2 of j prime v of x. Okay, these relationships, at least the first, second, and fourth, can all also be turned into integral relationships. I can simply integrate both sides, and then this to jv of x is equal to the integral of these dx. Same thing here and here. I can turn these derivatives, I can remove them by integrating, and then it's equal to the integral of the other side. This one doesn't really have an integral relationship because you integrate both sides, and it just changes it from its current relationship into an integral relationship, right? How do you use these? Well, basically, these are used a lot like we would use trig identities in order to prove trig, realities of trig equations. So here's an example of a problem like that. So let's get rid of all this. And this is typical of tonight's homework. They basically are saying, hey, prove that j2 prime of x is going to be equal to 1/2 the quantity of j1 of x minus j3 of x. And basically we had that property, I think it was property D, and what property D said was 2 of j any v of x, I'm going to say 2 prime, was then equal to j of v minus 1, which would be 1 of x, minus jv plus 1, which would be 3 of x. And of course, in order to make this line match this one, all we do is divide through by 2. So you'll get j2x prime is equal to 1/2 times the quantity j1x minus j3x. So it's utilizing those differential properties we learned in order to prove statements like this. Well, why would you want to prove a statement like this? Well, it turns out that there's going to be relationships, equations that we write like this that will be part of solutions to other differential equations. So being able to work through relationships that don't necessarily have rules governing them by using relationships that do have rules governing them are going to allow us to solve equations like this for what the values are. Okay, so that's basically where we're going to take this stuff after chapter 5. All right, so fortunately the homework then is pretty easy. It's really the application of those 4 rules. The second video that I posted is a little longer, and it talks about the Bessel functions that are based on half integer values. So watch through that. It's one of those faculty of Khan, and he does a pretty thorough job showing you that those actually turn out to be explicit functions and not infinite series.